Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to be going through section 9.5, linear equations. So, up to this point, we've talked about some first-order differential equations, the ones that have just some function and one version of its derivative. So not the second derivative, not the third, just the first derivative. That's what we call first-order differential equations. And we talked about how to deal with the separable ones in section 9.3, where we simply just try to get all dy's on one side, as well as the y variables, and all dx's and the x variables on the other side. If we could do that, then we can very easily just take an integral of both sides, and those are pretty simple to do. However, there are a plethora of other first-order differential equations that are not solvable in that way. What we're going to talk about is how to deal with a lot of the other ones that you cannot separate, and those are going to be the linear equations here. We have a few different examples of them. We have dy dx plus x squared y equals e to the x. Notice here we have this plus x squared y term. That's the one that makes it really hard in order to split all the x's to one side and all the y's to the other. We could subtract x squared y to both sides, but how do I move just a singular y back to the other side? That's difficult. We also see that same thing when we have this combination there and this plus 5y. All of these are very hard to get x all on one side and y all on the other side. However, if we notice, a lot of these, particularly if you consider the dy dx something like a constant, this looks a lot like a linear equation, a mx plus b situation, where y is an amount of slope, dy dx is an amount of constant, and then you have some x's and a function, e to the x. So this is similar to a linear equation, and that's why we call, or at least a linear function, and that's why we call them linear equations. Now, more generally, what these look like is right here. You have a differential plus some amount of x times y equals b of x. Again, not all first order equations will always look like this. We can maneuver a lot of them so that they do, and if they do form like this, we actually do have a very sneaky way of solving them. What we do notice as well, looking at this, is that we have dy dx as well as y. And then we also have a of x and something missing here. This looks a lot like the product rule, where we would have the product of two things. When we take the derivative of them, we would have the derivative of the one, and then the normal version of it. And then we have some function, I guess a of x would be the derivative of something, and then the other function that would be in front of dy dx. In order to make this look like a product rule, something like what we have written right here, what we need to do is introduce a new function, what we're going to call the integration factor ix. This is going to be our integration factor. What we want I of x to be is such that if I multiply it by a of x, I get the derivative of that. The reason I want that, I will show right here. If I take my original form, as I have written at the top, what I'm going to do is multiply by that integration factor, again, such that if I multiply that integration factor by ax, I get I prime, or the derivative of I. If that holds true, let's see what happens. First, I'm going to start with dy dx, and I'm just going to write that very simply as y prime, because I get tired of writing dy dx, plus ax y equals bx. And what I'm going to do is I'm going to multiply both sides by my integration factor of I. Both sides of the equation. What I get from that is y prime times ix, if I distribute. And then if I distribute again, we develop that I times a will give you the derivative of I. So then this is really y times I prime of x equals b of x, I of x. So now this looks exactly like the product rule. I have the derivative of one times the other plus the one times the derivative of the other. That's the product rule. Or y times I of x. Again, y would be some function of x prime equals b of x ix. Nice. That prime really means d of dx, or the derivative of it. That's really what that prime indicates. And so what we can do is take the integral of both sides. What that will give us is y times I of x equals the integral of bx ix dx. And then, since I evaluated an integral on one side, that means I'm going to get an arbitrary constant from it. Let's put that over here on this other side, because my goal here is to try to isolate what y is going to be. My overall goal is always to find what y is. Now the last thing I need to do is get y by itself, so I simply need to divide the ix over. So what I'm going to get is y equals 1 over ix times the integral of bx ix dx plus c. And that's what I'd be looking for. That now solves this first order equation where I can solve for y as a function of x's. One of the most important things to realize here, a very common mistake, is that this 1 over ix is multiplying not just the integral, but also the arbitrary constant. So that if you were to multiply this out, this would look like y equals 1 over ix times the integral of bx dx, or bx ix dx, plus the constant is also going to be divided by ix. So you're going to need to be careful of that. That means that constant is not just going to be by itself. It is also going to be divided by whatever the function ix is. Very, very common mistake. Remember that we do that because we did evaluate this integral here. We did solve this one. We got it by itself. But that's going to be our solution set. Now, all this hinged on the function ix, and we needed ix to be a function such that if I multiply by ax, I get I prime. Well, we need to figure out what ix is then, because if we're going to solve this for any general equation, we need to be able to evaluate what ix is. We can't just guess and check constantly. So we need to figure out what ix is in any given situation. Thankfully, because of this phrase that we set ix to be, we should be able to solve for ix itself. What I have here is the derivative of ix, which is d of ix, really. So if I write that down over here, I have ix times ax, the function that's multiplying y in my first order equation, equals I prime of x, which is the same thing, really, as the derivative of I. So I'll just say di. And if I get ax by itself, I get ax equals di over I, or I of x. Well, I can get rid of this derivative by making an integral of both sides. And what I notice is I have the derivative of I over I. It's really the same thing as like du over u. And if I evaluate this integral, ax dx, if I evaluate this integral here, I get the natural log of ix, whatever that I is. And then, to evaluate I completely, I could take each side to a power of e. And what I have is a solution for the integration factor, the key piece I'm going to need, and that is e to the integral of ax dx. That's what I'm going to need to solve for the integration factor. And if I look back at what I had, that actually makes sense anyway. When I take the derivative of something, I get that thing right back, as well as another function. That makes sense to be e because when I take the derivative of e, I get that function back. But I would probably be multiplying by the product of whatever was up top. This looks like the derivative of e anyway. But these are going to be my key pieces. I'm going to need to know what the integration factor is, and I'm also going to need to know the basic form of these integrals. So this right here. If I know what Ix is, I should be able to go directly to this form. We're going to do a couple examples though. In the first one, I'm going to show how that form would come about using these same steps. So you can see how this process would work without just arbitrary functions. Okay, also one last note, don't worry about a constant with I of x. With this integral of ax dx, you don't need to worry about a constant. Okay, so we're going to solve the following differential equations. So we have dy dx plus 2xy equals x. So we have this in the original form. We have this in the form of dy dx plus axy equals bx. It's already in this form. In this case, 2x is my a of x, and x is my b of x, so I don't really need to move anything. However, I recognize this as a linear equation, and so what I'm going to need to do first and foremost is solve for my integration factor. So I'm going to solve for what I of x is, and that should be the e to the integral of ax dx, where ax is 2x, this piece right here. There we go, 2x. So that means I have e to the integral of 2x dx. That's a pretty simple integral. That's e to the x squared. So that's what ex, or that's what the integration factor is. So, like I did in my original evaluation, I'm going to multiply both sides of this equation by ix. So, ix on this side, and then ix on this side. That's how I originally evaluated what ix is going to give me as a general form. But we're going to show how this would work itself. So if I multiply both sides of the equation by ix, I get dy dx. I'm just going to start to write this as y prime because it's easier for me. So y prime e to the x squared plus, I'll put y, and then I'll group the 2x e to the x squared together, and then I'll have x e to the x squared on the other side. This itself is a product rule. I have y prime and y, one derivative and the other, and then I have the function e to the x squared and the derivative of e to the x squared, which is e to the x squared times 2x. So this is going to give me the derivative of y e to the x squared is equal to x e to the x squared. And that's when I can take an integral of both sides. That will leave me with y e to the x squared equals the derivative of this side. I could set u to be x squared if necessary, du to be 2x dx. Divide the 2 over. I get 1/2 e to the x squared plus c. And then, if I divide e to the x squared over, note I need to divide the entire thing, which includes the arbitrary constant. I get y equals 1/2, because e to the x squared divided by e to the x squared will cancel out, plus c over e to the x squared, or how I'm going to write it, c times e to the negative x squared. That way I use less fractions. So that would be my solution for y. Note that if this, some of these situations will also have initial value problems, so they'll give you an x and y coordinate, and it would work just like it did in section 9.3, where you plug in values for x, plug in values for y, and you can evaluate c. Same process. But that's it. Note that we did this the long way. We didn't need to. We could have just used that original formula from the previous page. Y equals 1 over ix times the integral of bx ix plus c. We could just do that 1 over ix. In this case, where ix is e to the x squared, that would give me e to the negative x squared times the integral of x e to the x squared dx plus c. Well, that integral of x e to the x squared, I just solved that before. That'll give me 1/2 e to the x squared plus c. And that gives me the exact same formula. So we're all set. Okay, so I wanted to do one where I show how the integration factor would step by step get to that answer. However, in the future, what we can use is this formula as long as we know what I is and attempt to solve those integrals. Again, note that this will not solve every single linear equation in existence simply because bx ix could result in an integral that's not possible to solve. However, we have a lot of methods to our disposal. Notice that that's bx ix, a very common thing that you can use because that's a multiplication of two functions, is by parts. So remember that things like by parts and trig substitution all apply, particularly u substitution. That's going to be one of the most common ones. So we should have a lot of tools to solve most of these integrals. Okay, let's do another example. I have 4x cubed y plus x to the fourth y prime equals sine cubed x. All right, this one's going to be a little bit silly, and you'll notice why in a moment. But right now, we have y prime multiplying something. We need to get this in the form of y prime plus ax y equals bx, meaning we need to get y prime by itself. So I'm going to divide everything then by x squared, or x to the fourth rather. So this by x to the fourth, this by x to the fourth, this by x to the fourth. And some of you may already see what's going to happen with this. So I'll use a red pen just for difference now. We have 4x cubed y divided by x fourth will give me 4 over x y plus y prime equals sine cubed x. I'll put the x to the fourth first. So I'll say 1 over x to the fourth sine cubed x. There's no reason for this. I just like to write it that way. And now we have y prime by itself. That's what we need. That means that this function here is ax, and this long function here is my bx. Since this is now in the linear form, I can now try to solve for my integration factor, which is e to the integral of ax dx. Here, ax is 4 over x dx, and that's going to give me the 4 times the natural log of x. 4 times the natural log of x can move the 4 up to an exponent of x by the power rule, and e and natural log cancel, and this just becomes x to the fourth. So the integration factor is x to the fourth. That means if I take the general form, which remember the general form is y equals 1 over ix times the integral of bx ix dx plus c. If I take that general form, that means that I'm going to get that y is equal to 1 over x to the fourth times the integral of bx, which is 1 over x to the fourth sine cubed x, times ix, which is itself x to the fourth, dx plus c. That means those two are going to cancel out. And so all I have here is 1 over x to the fourth integral of sine cubed x plus c. dx plus c. Okay. The reason I said some of you may already notice what's happening here is because if we look at our original function, x to the fourth, the derivative of x to the fourth is 4x cubed. So it basically was already set up, or mostly anyway. Alright, so all we need to do then is figure out how to evaluate this integral. That will take a little bit of work, but not too terribly much. We notice that this is a trig function integral, and with an odd power, that makes it nice and easy to solve. We're going to replace two of the signs, so sine squared with 1 minus cosine squared. Leave a sine of x left over as my differential piece. If I set u as sine of x, or actually cosine of x rather in this case, cosine of x, I get du is negative sine x dx. And so y is 1 over x to the fourth times the integral of 1 minus u squared, actually negative integral, du plus c. So y equals 1 over x to the fourth times negative, this 1 is going to turn into a u, or a cosine. That minus and that minus will cancel out, so I get plus, there'll be 1/3 u cubed, u being cosine, so that's cosine cubed x, plus my constant. And if you want to multiply that out, you get y equals, if I put positive terms first, which I like to do, 1 over 3x to the fourth cosine cubed x minus 1 over x to the fourth cosine x plus c over x to the fourth. Again, don't forget that this c is also going to be multiplied by the integration factor. And that would be our solution. Okay. So notice we did need to pull back on some of our knowledge from previous sections in order to solve that. But most of these aren't going to be too bad. They should be relatively straightforward to solve. They shouldn't be overly complex. Okay. Let's do a couple more examples. Here we have x y prime equals y plus x natural log of x. I've written this down multiple times, but it may also be good for you to write it down. The linear form is again supposed to look like y prime or dy dx plus ax dx equals b of x. I currently do not have that. This is the only term that includes only x, so that's probably going to be our bx or some version of it. But y is on that side. That means I need to move it to the other side. And furthermore, there's an x multiplying y prime, just like it was before. So we have a little bit of work to do. First, I'm going to subtract the y over. And then I'm going to divide both sides by x. So I get y prime minus, I'll say 1 over xy equals x divided by x will cancel, natural log of x. Keep in mind as well that this is supposed to be, not ax dx, sorry, axy. Keep in mind that's a plus ax, and this minus will count as part of ax when I do my integral. So I'm going to have to keep that in mind. All right, so now this is set up, I can find my integration factor. My integration factor I, maybe I'll do that in another color to separate it. I is going to be e to the integral of ax dx. In this case, a of ax is negative 1 over x. So I'll put the negative up front. Integral of 1 over x dx. That's a relatively simple integral. That's e to the negative natural log of x. Again, don't worry about a plus c. But if I move that negative up to the top by the power rule, I can now cancel out e and natural log, and I just get x to the negative 1, or 1 over x. So that's going to be my integration factor. Then, using the standard form, again, it would be good to just start writing this down constantly. The more you write it down, the easier it will be for you to remember it. The general form of this, we get y equals 1 over ix, which is going to be 1 over x, which is just going to be, I'll write it down, 1 over x, integral of b of x, which is my natural log of x, so natural log of x times ix, which is 1 over x dx, plus c. That overall, 1 over x is x times the integral of natural log of x 1 over x, so I'll say natural log of x over x dx plus c, and that's pretty nice to solve. We could set u to be natural log of x du as 1 over x dx, which is what I have. So this becomes x, forgot those parentheses, x times the integral of u du plus c. So that's x times 1 over 2 u squared, where u is natural log of x, quantity squared. Note that squared is multiplying the entire natural log of x, or it's affecting the entire natural log of x, so I can't pull it down. Plus c. Or, if I multiply the x out, I get x over 2 natural log of x squared plus cx. Again, I've repeated this multiple times, but do not forget the integration factor is also multiplying your constant term. All right, and that would be that one. Last standard example, and then I have a more applied one. Okay, we have e to the negative y sine x minus y prime cosine squared x equals 0. Okay, well, looking at this, I have a 0 term, which is kind of weird as a bx, and I have a y prime, which has some stuff on it, so I am going to have to isolate that. But what I notice is that there is no term that involves only x's, which means that I do not need to solve this as a linear equation, because it technically really isn't. The way I should solve this is as a separable equation. Don't go into a situation and assume it's going to be separable or assume it's going to be linear. Should always look out for this. I don't see any terms that involve only x, so that's my key to think that there probably isn't a way to make this linear. But separable seems okay. If I just add one side to the other, I get e to the negative y sine x equals y prime, which I'll write as dy dx, cosine squared x. The reason I write prime this way is because this identifies where the y's need to be and where the x's need to be. Y is on top, so that means y's are going to join here on the right side. So y should be over here. And dx is on the bottom, so that means dx is going to have to multiply to the other side. And so I want x's on this side. So that means I'm going to have to multiply dx over, divide the cosine squared. So I get sine of x dx over cosine squared x equals, if I multiply by e to the y or divide by e to the negative y, I get e to the y dy. Sine over cosine squared. Sine over cosine will give me tangent, and then 1 over cosine will give me secant. So this is the same as secant x tangent x dx equals e to the y dy. That's pretty nice because now I can take the integral of both sides. Integral of secant x tangent x dx equals the integral of e to the y dy. And the integral of secant x or secant tangent, we should know that as secant x plus c equals e to the y. Remember that we'll get a constant from both sides, but we can combine it just to 1. Then to get y by itself, we take natural log of both sides. And so we get y equals the natural log of secant x plus c. Note that the plus c, the constant, is inside of that natural log. I keep harping on this, but make sure you do the c the second you evaluate the integral. It may be influenced by other operations like it was here. But otherwise, that is it. That's all we need to do. Alright, so that covers a lot of these basic integrals. The first three were all linear. The last one was separable. Again, I do that because I don't want you to have the assumption going into any problem that one is separable or one is linear. You should always be on the lookout for either of those. Alright, we have one more question here. Alright, so at time t equals 0, a tank contains 4 pounds of salt dissolved in 100 gallons of water. So we have a little bit more of an applied example. Suppose brine containing 2 pounds of salt per gallon is allowed to enter the tank at a rate of 5 gallons per minute, and a mixed solution is allowed to leave the same rate, or leave at the same rate. Find amounts of salt in tank after 10 minutes, or find, I guess, the amount of salt. Alright, so you could think about this like, I don't know, we have, I usually think about like a tank like this, like a cylinder, and say we have some brine that's going into the tank, and then we also have a funnel going out of the tank. So going into the tank, it's containing 2 pounds of salt per gallon at a rate of 5 gallons per minute, and then the mixed solution is allowed to leave at the same rate. Notice that we don't know how much salt is really leaving. All we know is how much is going in, but not necessarily how much is going out. In order to solve this, we're going to define a few things. First, let's just define our variables as y and t. We already have the variable t equals 0. And then y we'll just say is going to be the amount of salt. And it'll be the amount of salt at time of t. Start to use black marker here. So at time of t, which I guess would be in minutes. Okay, since we see minutes, we see minutes, all these are in minutes. What we know then, we know if I plugged in 0 as 4 gallons of salt. So that means we know it starts at 4. Our goal is to find what happens when we have 10. We don't know what this is. That's our goal. Lastly, we also know stuff about how the rate of salt. We know the rate of salt is defined by how much is going in and how much is going out, specifically the difference of those two. So this is going to define how much salt is in there, or really the concentration of it. The rate going in minus the rate going out. The rate going in is relatively simple. The rate going in is given to us. It says that there is 2 pounds of salt per gallon that's allowed to enter the tank at 5 gallons per minute. So that's 2 pounds per 1 gallon. A little stoichiometry here. Times 5 gallons per minute. Per 1 minute. That will give us how many pounds of salt I have per minute. So it'll give me 10 pounds actually. 2 times 5. So that's 10 pounds per minute. Rate out, though, is a little bit more complicated. The reason why is because we don't know how much is leaving at any given time, but we have that defined as how much salt at time t. So we have that the amount of salt going out is yt pounds at whatever time we're at, out of the entire tank, which is 100 gallons. That's how much salt we have in the entire 100-gallon tank. And that is leaving, it says, at the same rate, so that's also leaving at 5 gallons per 1 minute. 5 over 100 will give us 1 over 20. So we have y of t over 20 pounds per minute. So therefore, for our general equation, we have dy dt, the rate of salt, is equal to rate in, rate out. Rate in is 10 minus how much is leaving, which is how much is there out of 20. Or even more simply, just y out of 20. That is a relatively simple equation to solve. All we need to do is make this linear. So we see dy dt. We just need to move the y over 20 over to the other side. So we can make dy dt plus y over 20 equals 10. Now this looks linear. We can say that the integration factor I is going to be e to the integral of a of x, which in this case is just 1 over 20 dx. So it's going to be e to the x over 20. Or, sorry, not x over 20. We're not using x's. T over 20. And then we have overall our equation then, using the solving or the solution from linear equations. We have 1 over I, so that's 1 over this, which will give me e to the negative t over 20 times the integral of b of x, which is 10. So 10 times e to the t over 20, which is I dt, plus c. Remember that that plus c is out there. It is going to also be multiplied by this. Let's get some more room here. That gives us e to the negative t over 20. This integral is not too bad to solve. That 10 we can move on the outside. And then when we take the integral of e to the t over 20, we're going to get e to the t over 20. And then we're going to also have to multiply by 1 over 20 plus c. So that gives us e to the negative t over 20. We'll actually multiply that out. E to the negative t over 20 times e to the t over 20 will cancel. 1 over 20 is 20 times 10 is 200. Plus c times e to the negative t over 20. So that would be our equation. However, that's not it, because we have overall, we want find the amount of salt in the tank after 10 minutes, and we know the initial value problem of y0 equals 4. So if we want to find y of 10, that means we need to find out what the arbitrary constant is using our initial value problem. So if I plug in 0 for t and 4 for y, I have 4 equals 200 plus c times e to the 0 over 20. E to the 0 is 1. So we get negative 196 equals c. So overall equation now is y equals 200 minus 196 e to the negative t over 20. And now if we plug in our number of 10 into t, we get y equals 200 minus 196 e to the negative 10 over 20 is negative 1/2. That will require a little bit of calculation. So 200 minus 196 e to the negative 1/2 will give you about 81.19 pounds of salt. So that would be our solution there. Okay. So let's review what we did. Just walk through all the steps we did here. We started off with our basically given information. We start off with what y is. So y is just how much salt is. We have the initial values, what we have, what we want to find, and then what the rate is, or how much salt is in there. Just the rate going in and how much is going out. There's nothing else influencing this tank. Then we were able to solve through everything, and we found a general solution. dy dt plus y over 20 equals 10. We found this differential equation, which we were able to solve as we recognize it as a linear. However, some of you may have noticed this. I'm going to write that again. So I'm going to write this equation we had again. dy dt plus y. It was plus y, right? Plus y over 20 equals 10. And what we notice about that is that that's not necessarily linear. If we had what we had before, technically, which was 10 minus y over 20, that's what we originally had, that doesn't necessarily have to be linear. That can be separable. We can rewrite this as dy dt equals 10. If I put that over 20, we get 200 minus y over 20, because 10 is 200 over 20, just multiplying top and bottom by 20. And then I can divide the 200 minus y over and multiply the dt to the other side, so basically a cross multiplication. And what we get is dy over 200 minus y equals dt over 20. That's separable. We can take the integral of both sides now. This is going to give me natural log of 200 minus y, but also technically the negative of it because that was a minus y there. So you could do u du if you want to check that. Equals, this side is just going to give me t over 20 plus a constant. If we multiply negative to the other side, we get natural log. Actually, if we put the negative on the inside here, we could say natural log of 1 over 200 minus y equals t over 20 plus c. Take e to both sides. That gives us 1 over 200 minus y equals, equals e to the t over 20 plus c. That plus c, though, is a constant, which we've done that before. That can be pulled out here, because that would be e to the c, which is a constant itself. And then we could do some manipulation. Take the reciprocal of both sides. We get 200 minus y equals 1 over c is just a constant. 1 over e to the t over 20 is e to the negative t over 20. Starting to look familiar. Subtract 200. And then multiply by negative 1 on both sides. And we get y equals positive 200 minus c e to the negative t over 20. And we get the exact same formula we ended up with earlier. 200 minus c e to the negative t over 20. And this one, well, the only difference here is actually that it's a plus c, but that's not really important because c is an arbitrary constant. What this actually already noticed is that c was going to be negative, and we ended up being 196. So when we solve for c here, it would end up just being a positive 196 because we already got a negative there. So, same solution, because c is an arbitrary constant. Alright, so I wanted to show that that is possible to solve in multiple different ways. If you run into a problem like this, you usually can solve it either way, whichever one is easier for you, if you like separable or if you like linear. But overall, this is as far as we're going to go in Calculus 2 for differential equations. You'll go deeper when you actually go to the differential equations course about how to deal with other types of differential equations. If you have any questions, feel free to put those in the comments below or ask your instructor directly. But with that said, I hope you have a nice day.